Hey everyone! Welcome to today's video! In this deep dive, we're exploring dark matter, one of the biggest mysteries in modern astronomy and cosmology. You've probably heard that stars and galaxies rotate differently than we would expect from the visible mass alone, or that most of the universe's matter is invisible to our telescopes. But what exactly does dark mean in this context? Is it some exotic type of particle, or do we need to change our theories of gravity? And how do scientists even know dark matter exists if it emits no light? If you're excited about cosmic puzzles and want to learn more, you're in the right place. Make yourselves comfortable, hit the like button, subscribe to this channel for more fascinating science topics, and if you have friends who love space mysteries, share this video with them. Let's journey together into the hidden side of our universe, dark matter. What is dark matter and why dark? Dark matter is the name we give to a hypothetical form of matter that doesn't interact electromagnetically. It doesn't emit, absorb, or reflect light, or other forms of electromagnetic radiation. For all practical purposes, it's literally invisible. We only know it exists due to its gravitational effects on visible matter, radiation, and large-scale cosmic structures. Current estimates suggest that about 85% of all matter in the universe might be composed of this hidden substance. If we sum up everything we can see, stars, planets, gas, dust, even black holes made of ordinary baryonic matter, it still amounts to only a small fraction of the total mass required to explain certain gravitational phenomena. The rest is something we can't detect directly with our telescopes. When we say dark, it doesn't imply evil or sinister. It's simply dark in the sense of not detectable by light-based observation. Some might call it transparent or invisible matter, but the term dark matter stuck, emphasizing our lack of direct observational clues through light. Early clues: galaxy rotation and the missing mass. Problem: the idea that there might be some hidden mass in the universe gained traction in the 1930s, when Fritz Zwicky studied clusters of galaxies, notably the Coma cluster. He observed that galaxies moved so quickly within the cluster that they ought to have escaped its gravitational pull if only visible matter were present. But they stayed bound. So he proposed there must be extra unseen mass. Decades later, in the 1970s, Vera Rubin and collaborators measured the rotational speeds of stars in spiral galaxies. For instance, in the Andromeda galaxy, they expected the orbital velocity to drop off with distance from the center, much like in our solar system, where outer planets orbit more slowly. Instead, the outer regions of the galaxy rotated nearly as fast as the inner regions. This was inexplicable if only visible mass were present. By Newtonian dynamics, stars that far out should have flung away or moved slower. The solution: each galaxy might be embedded in an extended halo of invisible mass, now referred to as dark matter, providing the additional gravity to hold those stars in place. Gravitational lensing, bending light as further evidence. A second powerful line of evidence for dark matter comes from gravitational lensing. According to Einstein's general relativity, a massive object, like a cluster of galaxies, can bend the path of light from a more distant source, a quasar, say. This can create multiple images or distorted arcs, known as Einstein rings. By analyzing how strongly the background light is curved, astronomers can infer the total mass distribution in the foreground object. Time and again, these observations show far more mass than is visible in stars or hot gas alone. In other words, something invisible contributes significantly to the gravitational pull. That hidden component is what we call dark matter. The bullet cluster, a striking demonstration. One of the most dramatic pieces of evidence is the bullet cluster, 1E0657, 558. This system consists of two galaxy clusters that have collided. During the collision, the hot intergalactic gas, visible in X-ray observations, slowed down and remained near the center of the impact, while the galaxies themselves passed relatively unimpeded. Galaxies are mostly empty space, so direct collisions among them are rare. When astronomers map the mass distribution via gravitational lensing, they find that the bulk of the total mass traveled with the galaxies, not with the slowed-down gas. This strongly suggests that much of the mass is in a form that barely interacts, except gravitationally. If all the mass were in ordinary matter, the gas and visible stars, we would see the mass remain where the gas is. The bullet cluster thus provides an impressive visual snapshot, indicating that some other stuff moved along with galaxies and parted ways with the normal gas, the hallmark of collisionless dark matter. What could dark matter be? Leading candidates. If dark matter isn't regular atomic, baryonic matter, what might it be? Several hypotheses exist. WIMPs, weakly interacting massive particles. Proposed heavy particles that primarily interact via gravity and the weak nuclear force. A prime example would be a supersymmetric partner particle, for example, the neutralino. Axions, extremely light particles suggested to solve certain issues in quantum chromodynamics, QCD. If axions exist in huge quantities, they could account for a major fraction of the universe's total mass. Sterile neutrinos, a hypothetical kind of neutrino that doesn't even participate in the weak interaction, only gravitationally. Macroscopic objects. Some theories propose primordial black holes from the early universe. However, current data imply that such black holes can't make up all dark matter. Searching for dark matter. Deep underground and particle colliders. How do you detect something that doesn't interact with light? Physicists have built ultra-sensitive detectors placed deep underground, in mines or tunnels, to reduce cosmic ray interference. The idea is that if a WIMP or another dark matter particle occasionally collides with an atomic nucleus in the detector, it would deposit a tiny amount of energy that we can measure, a faint flash or a slight recoil. So far, no unequivocal signal has emerged from these experiments, though a few anomalies sparked excitement. In parallel, particle physicists at accelerators like the Large Hadron Collider, LHC, and CERN are looking for exotic processes that might hint at dark matter production. Alas, none of the simpler supersymmetric scenarios have been confirmed yet. Alternate theories. Could gravity itself be wrong? Some researchers argue that instead of postulating new forms of matter, we should modify the laws of gravity. For instance, MOND, modified Newtonian dynamics, adjusts Newton's equations at low accelerations, which might explain the flat rotation curves of galaxies without invisible mass. While MOND provides interesting fits for certain galactic phenomena, it struggles with cluster-scale observations, like the bullet cluster, and strong gravitational lensing. Therefore, the majority of cosmologists remain convinced that an unseen dark matter component is truly out there, rather than an error in gravitational theory. The LAMDA-LCDM model. The standard cosmology, one of the most successful frameworks for describing the universe's evolution, is LAMDA-LCDM, which stands for Lambda Cold Dark Matter. Lambda refers to the cosmological constant linked to dark energy. CDM means cold dark matter, non-relativistic or slow-moving matter on cosmic scales. In LAMDA-LCDM, only about 5% of the universe's total energy density is normal, baryonic matter. Around 27% is dark matter, and the remaining 70% or so is dark energy. This model explains key observations, like the cosmic microwave background, CMB, large-scale structure, and galaxy cluster distributions, if we accept that dark matter is real and exerts crucial gravitational influence. Why does it matter for us? While dark matter might seem purely abstract, it deeply influences cosmic evolution. Our own Milky Way galaxy is believed to be embedded in a vast dark matter halo that stabilizes its rotation. If dark matter didn't exist, galaxies might have dispersed long ago, or they wouldn't have formed in the same way, potentially changing the entire cosmic story, including the environment where planetary systems and life arise. On a more fundamental level, discovering the nature of dark matter could revolutionize physics. Identifying a new type of particle would fill gaps in our standard model of particle physics. Meanwhile, continued failure to detect it might push us to radical new gravitational theories. Either result opens big questions about how the universe truly works. A cosmic puzzle still unsolved, dark matter stands as a profound enigma. It's invisible, intangible to electromagnetic means, yet shapes galaxies and clusters, distorting light and dominating large-scale structure. Observations of rotation curves, gravitational lensing, and systems like the bullet cluster collectively point to something massive yet elusive. Scientists persist in refining underground detectors, scanning data from telescopes, and exploring high-energy collisions for any telltale signature of dark matter particles. If we ever discover a conclusive candidate, be it a WIMP, an axion, or something else, It will mark one of the greatest triumphs in physics, on par with relativity or quantum mechanics. Thanks for joining me on this cosmic exploration of dark matter. If you enjoyed this video, give it a thumbs up, subscribe so you won't miss our next deep dive into space and science, and share it with friends who love cosmic riddles. Let me know in the comments which candidate or theory you find most compelling. WIMPs, Axions, or maybe a modified gravity theory. I can't wait to hear your thoughts. Take care, and remember, our universe is full of hidden wonders waiting to be discovered.